Hi, Science and Cooking. So I thought that I would actually try a video for you in which I give a more advanced discussion of the topic of this week, namely heat transfer. So the topic of this is heat transfer, more advanced. I don't know if this is going to be useful to any of you, but I'll give it a shot and see how it works. Okay, so first I need to, so if we're going to give a more advanced description of heat transfer, the first thing that we need to do is to give a more advanced description of random walks. So you will recall in lecture that we talked about how a random walker moves to the right or to the left at equal probability. And so if we have a lattice, and here is the lattice, and if we were to label this point x on the lattice, and I called this point x plus a, and this point x minus a, so the spacing between these little elements is a, then the idea, remember, is that a random walker would start out at a position on the lattice and take a jump to the right or to the left with equal probability from one time to the next. So we can express this in mathematical terms. And to do this, we'll do the following thing. So let's suppose that the random walker takes a step every time tau. So tau is the time between steps. Okay, and the question that I want to ask is, what is the probability p that the random walker is at a position x at a given time? And just to make this easy, let's say at time t. Okay, so in order to be at position x at time t, then there are really two choices. At the previous time step, which was at time t minus tau, you had to be either at x plus a or at x minus a. And there's a 50% chance that you're at either one. So you were either, if you're at position x at time t, you were either at x minus a at time t minus tau, or you were at position x plus a at t minus tau. Those are the two possibilities. And so this is the equation basically that summarizes, in a nutshell, what a random walker does. And I can rewrite this basically as I can rewrite this. I mean, we could have done this from t minus tau to t, or we can do it from t to t plus tau. So I can rewrite it as p of t of x of t plus tau is equal to 1/2 of p of x plus a and t plus p of x minus a and t. Okay, and this equation is the fundamental equation that describes a random walker, and thus actually the heat transfer that occurs in a material and everything else. So okay, so now what we would like to do is to take this equation and analyze it, and because what we would like to do is find out what, so we would like to calculate, really, p of x and t. We would like to know what the distribution of random walkers is. Now, if we knew that, then we would also know, since the random walkers were either calcium ions, for example, in the instance of gelation as verification, and they are heat this week, from the point of view of heat transfer, this probability of where the random walkers are is essentially a proxy for whatever the temperature is at time x and t, and whatever the concentration of the nutrient, of the calcium field is. And so one would like a way of actually taking the equation, the fundamental equation for the random walker on the previous slide, and calculating either of these two quantities. Now, okay, so the next question is, how do we get insight from this equation? That is, this equation, which I've now just rewritten in this sort of typed form, is there. And the question is, how do we get insight? And the answer is unfortunately to do some algebra first, and to just derive the consequences of this equation. So the algebra basically goes like this. So the random walk has two parameters associated with it. There's the parameter a, which is the step size, and there's the parameter tau, which is the time between steps. And both of these parameters are very, very, very small. So for example, a is probably on the scale of, I don't know, nanometers or something, and tau is probably on the scale of nanoseconds. That's how fast the molecules in a liquid, for example, are moving around or transferring heat to each other. Whereas when we're cooking or doing anything macroscopic, the time scales and length scales that we're interested in are much different. So a piece of steak is, a centimeter in size, and it takes time scales of minutes for it to heat up. So A and tau are small, parameters. So for those of you who have taken calculus, when a parameter is small, you can do what we call a Taylor series expansion and expand the quantities in the above equation as a function of t and tau. And so, for example, we can write that p of x and t plus tau is equal to, according to a Taylor series, is equal to p of x and t plus tau times dp dt plus tau squared over 2 times the second derivative of p, which I will just write as p dot dot, and so on. And that is what is called the Taylor series expansion. So similarly, we can do the same thing for p as a function of x and t. So actually, let me just erase this. In fact, this might be the easiest way to do this. So let me erase this, and then we can write the same Taylor series expansion for p of x, expanding as a function of x. So if I write p of x plus a and t, then that is just p of x and t plus a times dp dx. This is going to be my notation for a derivative. That's dp dx plus a squared over 2 times the second derivative of p, and so on. And this is something that you'll learn in a calculus class. Now, if we take the three expressions that I just described and put them together, that is, we plug in the equation for p of x and t plus tau that we derived before, I take this equation and I plug it in right there. So namely, just to make sure you guys know what I'm talking about. So I'm going to take this whole expression right here in this box, and I'm going to shove it in the formula right there. And then I'm going to take the same expression where instead of deriving p of x plus a, I'm going to do p of x minus a. So I can make that a minus, in which case that becomes a minus. Everything else is the same, and I'm then going to take that and plug it in there. If I do that and I combine all of them together, then after some algebra, I get the following equation. The equation is that dp dt, I didn't change my color of ink, is equal to a squared over 2 tau times the second derivative of p with respect to x squared. And plus, there are other terms that come in, but they are all smaller than these two terms. And this is essentially what we get. And this is a famous equation, which is called the diffusion equation. And this parameter here, a squared over 2 tau, is the diffusion constant, which is what we've been calling in class d. Now, using this equation, I can now write down the diffusion equation for temperature. So I can write down one for temperature, or I can write down one for concentration. So since we're doing heat transfer this week, let's write it down for temperature. So the derivative of the temperature with respect to T is equal to a diffusion constant, the temperature diffusion constant, times the second partial derivative of the temperature with respect to X. And now, basically, if I'm given a hunk of food, like, for example, this week, I think the most interesting thing we discussed in the lecture today was Teston Blumenthal's method of cooking a steak. Basically, what he did is he took a piece of steak, and then he took a hot stove. So here's the hot stove. He put the steak on the hot stove, and he let it contact. So this stove is heated up to some temperature. I don't know what you can call it. Let's call it, I don't know, let's call this 200 degrees Celsius, but it's probably actually hotter. And the steak is initially at a temperature of, I don't know, it's at room temperature, so it's 20 degrees Celsius or something. And then basically what you do is you contact the steak with the hot plate, and heat then diffuses inwards into the steak. So this heat is going to basically diffuse in. This part is going to come hot. And then after 15 seconds, he turns the steak over and does it on the other side, and so on and so forth. And the question that we would really like to be able to compute, and actually, is, if one really wanted to do this in detail, is to please compute the temperature distribution in this steak as a function of space and time. And this, as it turns out, can be done quite elegantly and really quite precisely by solving this diffusion equation as a function of time. Okay, so at this point, I must admit to being a little confused about whether I should really continue and show all of you guys how to actually solve mechanically the diffusion equation for the Heston-Blumenthal problem or not. Maybe what I will say about the mathematics gets a little bit complicated, and I'm happy to discuss it, but I'd like to know if anyone got to the end of this video and found this to be useful before I do so. Maybe what I will say, though, is the following thing at this point, just to finish this off. So here is our piece of steak, and actually the way that we would set up the calculation is that we would assume the steak is essentially infinite in one dimension. So we would forget about the side boundaries of the steak. So we would have an infinite steak. And then what we would do is we would say that the steak is initially at a temperature, that we set of whatever, 20 degrees Celsius, and we would then say that this bottom boundary at the bottom is stuck to be at a temperature of whatever, say 200 degrees Celsius. And the question that we would ask is, given these conditions, how does the temperature in the steak evolve as a function of time? To make this work, to make this problem perfectly well formulated, we would also have to specify some condition about what the temperature in the air is. And I guess I would just say the temperature in the air is 20 degrees as well, because that's the reason that the steak is at room temperature, is because it's in contact with the air. And so what we would then do is we would take the equation, namely d, the partial derivative of temperature with respect to t, is equal to d times the second derivative of x with respect to t. X would be a coordinate that would go this way. This point here is x equals 0. And maybe we'll say the end of the steak is a distance L. That's the notation that we used in class. And then what I would do is to basically solve this partial differential equation for this setup of a problem. And this is something that one can do in great detail and actually find out how the profiles of the temperature would behave. I can tell you qualitatively what they would look like. Maybe then we'll stop for here. But if any of you are interested in learning more or having me do more calculations, I'm really totally happy to do this. I love calculating. It's just that for the most part of my life, no one cares. And so therefore it doesn't work. So this is the temperature as a function of x, and basically initially, remember, the steak is at temperature, which I will call this. I will call that 20 degrees. And then the edge is at 200 degrees or something. So there's this very, very initial profile where after just an instant of being in contact with the steak, the profile looks like this, where this is 200 and this is 20. And then what happens over time, here I'll change the color. So at a slightly later time, what happens is that this basically just spreads inwards. And the profiles look a lot like what I'm drawing here. It's basically a Gaussian profile for those of you who like functional forms. And the characteristic width that the solution has, that is the length scale over which the temperature is hot, is basically given by our favorite formula, the square root of 4 dt. And this is rigorously where the equation of the week comes from, solving the equations of motion. Okay, so that's it. That's all. If any of you found this useful, please tell me if anyone got to this point. I'm happy to make videos like this. I could keep going. I could explain more mathematics. I could explain the steps that gave to the random walk equation better than I did. I don't really know what's useful or what you guys are interested in, but like I said, this is not that hard to do, and it would be a pleasure if I could teach some of you more mathematics. Anyway, thank you.